Okay, so today we are going to talk about Lewis structures, hybridization, bone angles, and molecular and bone polarity of molecules. So right here we have a molecule called NH3, so we first have to draw the Lewis structure in order to find its hybridization, bone angle, molecular polarity, and bone polarity. So if you want to do that, first you have to know the number of electrons that it has. So here NH3 has 5 for nitrogen plus 3 electrons from um, hydrogen, and that's gonna be 8. So you will have a total of 8 electrons. So you have to get 8 electrons when you draw the Lewis structure. So N, H, 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 and then 2, 4, 6, 8. Okay, so we have 8 right here. So now we're good with the Lewis structure. So from the Lewis structure, first you have to find the electron geometry if you want to find its hybridization, and you want to find its molecular geometry if you want to find its bone angle. So the electron geometry, I'm just gonna abbreviate it as E, M, and MM. Sorry, EG and MG. So electron. Okay, so electron geometry is, so we have 3 bonding sites and 1 lone pair, so it's 3 to 1, right? So 3 to 1 is gonna be trigonal. So let me write it. So it's gonna be a trigonal planar. So not trigonal planar, I'm sorry, it's gonna be a tetrahedral. And the molecular geometry is gonna be a trigonal planar. So what this means is that, so our hybridization, so our, hold up. So our hybridization, this is gonna be hybridization, I'm just gonna abbreviate this as H, is gonna be sp3 because it comes under tetrahedral. So we found that, we are done, and then we have to find the bone angle. Or okay, and then we have to find the bone angle. We know that it's a tetrahedral, and we have a trigonal. Oh, it's basic. Sorry, I made a mistake. It's not trigonal planar. It's trigonal pyramidal. Okay, pyramidal. Okay, so then if it's a trigonal pyramidal, then our bone angle is gonna be somewhere around 109.5. But since it's the molecular geometry is not tetrahedral, it's our final bone angle is gonna be less than 109.5. So that that is our bone angle, I think. Okay, so around less than 109.5. Now, what about the molecular polarity? So just note that if there is a lone pair like this, it's definitely gonna be polar. So our molecular polarity is gonna be polar. Because when you have a um, lone pair, you cannot. It's when you cannot share electrons equally. So even if you if you look for the symmetry, for example, if you look for the symmetry, oops, sorry. If you look for the symmetry, then notice that this is not similar to this one because we have a lone pair right here. So even if you look for symmetry, they are not symmetrical because of the lone pair that they have. So molecular polarity is going to be polar, and our bone polarity, what about that? So for bone polarity, let me. So for our bone polarity, you're just gonna basically um find the difference of electronegativity. So for that, let's find the difference between that. So the electronegativity charge of nitrogen is, so the electronegativity charge for nitrogen is 3.0, and the electronegativity charge for hydrogen is 2.1. So you're just gonna find a difference. You're gonna subtract this, and you're gonna get, so it's gonna be 0.9. So after you find it, you're just gonna write the so you know that the 0.9 is basically gonna be, it's gonna be polar, because anything that's from 0.3 to 1.7, it's gonna be polar. So our bones are also gonna be polar. So that is how you find the bone polarity and molecular polarity for NH3. Okay, so now we're gonna talk about H2O. Okay, water. Okay, so let's talk about water now. For water, so for water, um, 2 plus. Okay, I'm sorry about that, but 2 plus 6 equals 8. So we need 8 electrons to satisfy the octet. To satisfy the whole molecule, for example. Yeah. So let's draw that. Okay, now when you see this, you notice that this has two bonding sites and two lone pairs. So it's a 2 to 2, which means that its electron geometry, it's gonna be tetrahedral. And molecular geometry, this should be a G. Okay, molecular geometry, it's gonna be um, bent. Okay, from this, what can you notice? Sorry, I forgot this two lone pairs. Okay, I mean the other lone pair set. Okay, now it's right. So we have two lone pairs, one over here and one over here, and two bonding sites, one over here and one over here. That means that it's a 2 to 2, so we have electron geometry. For the electron geometry, you can say that it is a tetrahedral, and for molecular geometry, you can say it's a bent. So when it's a bend, you could rub it, and you know what? I'll just rub it and draw it like in a bent way. So like this. Okay, this is how you draw it. Okay, so now we know that this is our electron geometry and molecular geometry. From this, what do you notice? You can say something about the bone angle from this information that we got. So from this information that we got, we could find the bone angle. So here, the bone angle is basically gonna be something around or somewhere around 109.5. So 109.5, right? So since it's a bend, the bone angle is the bone angle should be the bone angle sorry the bone angle should be less than 109.5. So this should be the bone angle. So I'll just write it over there, you know. Okay, so we got our bone angle, and now what else can we say from this? Okay, so we got our bone angle. Now, what else can we get it from? But what now, what else can we get from the molecular polarity? Well, there's a lot of things. The one of the things that we can still get is gonna be our hybridization, which I totally forget about. Okay, I totally forgot about hybridization. So this is hybridization. So for hybridization, it's basically just gonna be. I'll just abbreviate hybridization as H. So H equals sp3 since it's a tetrahedral. So hybridization is gonna be sp3. Cause why? Because the electron geometry is gonna be it's tetrahedral, so it should be sp3. Okay. Now, what else can we maybe like sort of get from this? Well, there's a lot of stuff that we can get. Uh, we got our first time we got our bone ankle, right? We got our bone ankle. We got our yeah. So we got our bone ankle. We got our hybridization. So we also could basically identify the polarity. So we could maybe say by just looking at the Lewis dot structure, we could say the bone polar. I mean, sorry, we could figure out the molecular polarity. So for molecular polarity, I'm just gonna abbreviate this as MP. So molecular polarity. I'm sorry, my handwriting is that not that good. So molecular polarity is gonna be based on what? It's based on a lot of stuff. So one thing, it's based on the lone pairs. So if you have lone pairs like this, so it's most likely to be polar. But there's also some other things that you have to keep in mind. For example, the symmetry. So as I said before, so when if you divide this like this, for example, you notice that the this thing is symmetrical to this thing. However, we have two lone pairs. So this definitely will not be symmetrical. It would be asymmetric or it would be asymmetrical. So since it's asymmetrical, there's chances that it's gonna be polar. And the other thing that we care about when you talk about the molecular polarity is dipole moments. So we all know that the oxygen is more electronegative, or if you don't know, just look at the periodic table, right? So it has more electrons. So oxygen is more electronegative than the hydrogen. So the dipole moment is going from here. So let's first write the sorry, that's happening. Okay. Let's first write the partial positive on hydrogens, and oxygen is partially negative. Okay, so the dipole moment is now going from positive to negative, so it's going like this, right? So like this and like this. Okay, so it's going from hydrogen to oxygen. But remember, it's a bend, so we still have this y going like this, because it's like, you know, it's a sort of bend. So, like, there's still this y axis going upwards and x axis going this sideways. So, what can we say about that? Well, if it's like that, now we could possibly cut out some things at least. So we could cut this one and this one because it's going opposite directions. We could probably cut this one and this one because it's not going like it's going to like it's facing in opposite direction, so it's like facing not towards each other, right? So we could cut this. However, we cannot cut this one because it's both are going upwards. So what happens is we still have that dipole moment. So the dipole moment is not zero. And since its dipole moments do not cancel completely, the molecular polarity is gonna be polar. So it's molecularly gonna be polar. Now what about the bond polarity? So for bond polarity, um, you have to basically find the electronegativity difference. So for hydrogen, we know that hydrogen. So for that, you know that, for example, hydrogen is 2.1, right? So hydrogen, we know that hydrogen is 2 point. So hydrogen is 2.1 hydrogen, and oxygen is 3.5, somewhere around, yeah, 3.5. So for, as we did before, we are just gonna find the electronegativity difference between hydrogen and oxygen, and that will give you an answer of 1.4, right? And we know that if something is greater than um 0.3 but less than or equal to 1.7, so it's still gonna be polar. So what it means that it's gonna be polar. So it's H2O is, or water is high, it's a high polar molecule. So that's how you find the bond polarity. Okay, so that is it about hydrogen. I mean, water, right? That's about H2O. We found it. So that's how you find the molecular polarity, bond polarity, hybridization, bone angle, and those sorts of stuff. And of course, if you have to find all these stuff, then you have to draw Lewis dot structure, and you have to find the electron geometry as well as the molecular geometry. Alright, so that's basically it for hydrogen, or I mean, water molecule, or H2O. Now, let's talk about another one. Okay, so now let's talk about carbon dioxide. So, obviously, we are just first to draw the Lewis structure, obviously we have to find the total number of electrons. So carbon has 4 electrons, so 4 plus, and oxygen is 6 times 2, 12, and that's gonna give us 16, right? Okay, so we have to get 16 total. So let's draw the Lewis structure now. So carbon side, oxygen, 2 oxygens. Okay, so 2, 4, 6, 8, 10, 12, 14, 16. But since we are trying to make it symmetrical, we are gonna put, okay, so we are gonna put doom boom. So 2, 4, 6, 8. And we are gonna rub this one right here. I'm gonna put it over here. Okay. Okay. So now 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay. Notice that all these, so when you just sort of like divide it for example, it's symmetrical. So it's basically very, very symmetrical. Everything is shared equally. So we now know that information from this Lewis structure, but yeah. So from this, now since we have 2 bonding sites and 0, so let me write it over here. So 2 bonding sites in 0 lone pairs on the central atom. It's a 2 to 0, so meaning it's gonna be linear. So it's a linear meaning the molecular geometry is gonna be linear and the electron geometry is also gonna be linear. So what that tells about our bone angle is that our bone angle is gonna be somewhere around. So let me write that. So here's the bone angle, right? So our bone angle is gonna be a straight 180 degree. No lesson and stuff. It's just gonna be straight 180 degree, right? That's our bone angle. Okay, we found our bone angle. So this is our bone angle. I'm just gonna. Yes. So this is our bone angle. Okay. So we found our bone angle. Or, yeah. So now what else do we have to find? So we know that our bone angle is a 180 degree and it's linear and it's symmetrical. So from this information, oh, before that, what about the hybridization? So for hybridization, I'm just gonna abbreviate this as H. Okay. It's SP1 or just SP because it's a linear, which will come in, or in the electron geometry it's a linear, right? So for anything that's linear in electron geometry is gonna be always in SP. So hybridization is SP. We're done with that, and we still have to find out some more stuff. And one of them is molecular polarity. So I'm just gonna write it over here. So for molecular polarity, what you notice is that you know that it's symmetrical. So let's, from this information first, let's write the information. It's symmetricals. Okay. And let's check its dipole moment. And oh yeah, no lone pairs on the central atom. That's an information that you can. Right. Okay, no lone pairs. And let's check the dipole moment. So it's going from. So it's since carbon is more positive, so it's gonna be a positive, and this is gonna be a negative. All right. And so now the dipole moment is going from a positive to negative, right? So like this. Oh, sorry, that was bad. Like this and like this. So it's going from a positive to a negative. Okay, this is going like that, and it's linear. So it's going the other way, right? So if it's going the other way, it's obviously gonna cancel out. So let me use another color. So it's obviously gonna just cancel out and it's gonna turn into, so I will just write it over here. So the dipoles cancel. So dipoles cancel, right? So dipoles cancel. These are the information that we know. So from these informations right here, what can you conclude is that the molecular is non-polar? Because remember, if the molecules are non-polar only if the um, Lewis structure or the molecule is symmetrical, it has no lone pairs, and the dipole should cancel and the net dipole moment should be zero. And right here we have no dipoles left, everything got cancelled, and so we can finally conclude that it is a non-polar molecule. So non-polar molecule. Okay, now what about our um, bone polarity? So for bone polarity, my handwriting is not good. Okay, so for bone polarity, as we said before, we're just gonna take a look at the electronegativity charge. We're just gonna find the difference. Okay, so oxygen's electronegativity charge is 3.5, and carbon's electronegativity charge is 2.5. So we are gonna subtract 3.5. I mean, we are just gonna subtract the electronegativities of these molecules right here, and we're gonna get a 1.0. Okay, so since the 1.0 comes under polar molecule according to the measurement, or according to the electronegativity measurement scale, or polarity measurement scale. Actually, yeah, there's polarity measurement scale that you probably have to know. So it's from, if it's from 0.3 to 1.7, it's gonna be polar. So it is polar. Okay, so that is it. That is how you find electronegativity, bond polarity, and molecular polarity for carbon dioxide. Okay, so this one is a lot of tricky. Some For a lot of people, it's a trickier one. So I really wanted to do it. So yeah, that is it. I worked 3 examples for you guys, and I hope it was more of like a good, or like, and I hope I was able to explain a lot about this ones. But yeah, so these are the 3 ones that I really wanted to discuss today in this video. So this is just part 1. I really want to discuss other 3 or 4 ones, so I'll do it in the next video. So thank you so much, have a nice day. So part 2 is coming on the way, so if you have any questions, just comment below and I'll answer it, or I'll do a separate video about that question. Okay? So thank you so much and have a nice day. Thank you.